Hi, everyone. So today I'm going to tell you about the new methodologies that we are exploring here at Microsoft Research to train large language models. This is joint work with a really fantastic team. You can see all of the co-authors here on this slide. And the name of the methodology is Textbooks Are All You Need. So let's jump right in. So this methodology, we are currently applying it to train new large language models. And we have two of those models that I will talk about today. This is the first batch in a series of models that we hope to create with this new technique. The first one is Phi1, and the second one is Phi 1.5 that we just released very, very recently. Both of those are small large language models, small at least by the standards of today, with only 1.3 billion parameters model. So what are those models? Phi1 is a coding model with performance that we evaluate to be comparable to models that are roughly 10 times bigger and trains on data sets which are more than 100 times bigger. So 3 orders of magnitude gains for Phi1 for coding specifically and coding in Python. Phi 1.5 is our technique applied to natural language. And there we estimate that roughly Phi 1.5 is comparable to models that are 10 times bigger and trained on at least 30 times more data. And moreover, this is performance in terms of natural language. But if you go to reasoning and specifically coding and mathematics, Phi 1.5 should be compared to models that are probably more like 50 times larger. And I will come back to this later in the presentation. I'm first going to focus on Phi1 and coding to explain the textbooks are all you need methodology. So first, let me just backtrack for 1 second. What are we talking about with large language models for coding? Well, we're talking about things like Copilot, where you give the beginning of some code, and then you ask for basically a completion of the code. This is what those large language models for code are doing. Okay, so we're going to tell you a new models like this with only 1.3 billion parameters that does this kind of code completion very well. Now, the natural question is, how do you evaluate the performance of an LLM on code? And there is a quite standard benchmark by now from OpenAI called HumanEval. So this is one way to evaluate coding models. This is 164 handwritten programming questions with unit tests. So each of those programming questions comes with a set of unit tests, and you say that you have solved the task if you can pass all of these unit tests. What do those programming questions look like? They look like this. You get a name for the definition of the function, like increase list, and then you get a doc string explaining to you what, in natural language, what the function is supposed to do with maybe some example. And now the goal is to complete, to write the code that does what the doc string is asking you to do. Okay, so here, just 2 examples. One where you have to return code that, given a list, increase all elements by 1. And this other one is given a list of integer, return the sum of all the odd elements that are in even position. So you see, these code completions are very easy. It's just 1 line of code. So this is very simple. But in the HumanEval benchmark, there are also much more difficult coding questions. Now, let's look at the progress that have been made on this benchmark in the last couple of years. As you all know, AI has made incredible progress recently. Let's see how it looks like in action on the specific task of coding and specifically HumanEval. So HumanEval was introduced again 2 years ago in July 2021 by OpenAI. And at the time, they created also 2 models, the Codex series of models. And these were coding large language models. And here I'm giving you 2 examples. One is a 300 million model, and one is a 12 billion parameters model. So you see here is the model size. Both of those models were trained on 100 billion tokens. Okay, so this is the size of the data set. And what scores did they reach on HumanEval? Well, the 300 million only got a mere 13%, while as you scale up the size of the model, you get this amazing, fantastic magical behaviors that as you scale up the model, the performance improves, and you can see a huge jump to almost 29%. Okay, so this was 2 years ago. So what happened since then? Well, shortly after, something interesting happened. These folks at CodeGen, they created a model trying to mimic OpenAI, but they open sourced their model. they obtained very similar results. You see that at 350 billion, they also got 13%. At 16 billion, they got the 29%. They had a data set much bigger, 500 billion tokens, yet no real improvement in terms of the HumanEval. Now, after that, things started to heat up a little bit, and you can see the big model started to emerge with Palm Coder, specifically 500 billion parameters, a much bigger data set. We are now nearing the 1 trillion token, 780, and you get again a little boost. But you see some kind of diminishing return. We moved from 300 million to 12 billion. We got a 2x improvement from 13 to 29%. Now you move to 12 billion to 500 billion, and you only get an improvement to 35%. So maybe some kind of little diminishing return. Of course, GPT 3.5, we don't know the size of the data set, but this is 175 billion parameters, and this reaches an amazing 47%. Other models, you see they are increasing the size of the data, and you get very little improvement. Here's the Santa coder. It's interesting because it's 1 billion parameter, like the models that I will tell you about, and it reaches only 14%. But then, of course, GPT-4 happened roughly 6 months ago, and this made an amazing jump to 67% on HumanEval. And in fact, this is a version that was released in March, but the version we had access to in Sparks even got a higher score. So GPT-4 really kind of cracks the problem. Now, shortly after GPT-4, things really started to heat up. And we see that we have new models coming out every month. In fact, in May, we have like many models that came out, and they all share roughly the same characteristic. You see that the data sets, they are huge, 500 billion, 1 trillion, some of the recent ones here are slightly smaller, but the models are all big. 15 billion parameters, you get in the 30%, 16 billion parameters, you get again in the 35%. So you see it's all roughly in the same ballpark, maybe with Wizard Coder being the exception, which is a jump at 16 billion parameters, 1 trillion tokens, it gets to 57%. Now, let me tell you what we did. With Phi-1 and the textbooks are all you need approach, which I will explain in a minute what it is, here is the result that we got. We have a much smaller model, only 1.3 billion parameters, a data set which is incomparable to those other data sets, only 7 billion tokens, yet we reach 50.6% accuracy. So except for GPT-4 and for Wizard Coder, this is the best in this table, despite being so much like 3 orders of magnitude smaller. And moreover, we're going to talk about whether we were overfitting to HumanEval. This is a very natural question. We will talk about it a little bit later, but I can already give you another benchmark, this MBPP, mostly basic Python programs or Python puzzles. We get 55% there, which is higher, for example, than Wizard Coder. So this is just a small indication right now that we're not at least overfitting to HumanEval. So now let me explain to you what we did. What is this textbooks are all you need approach? And for that, let me just backtrack 1 second. What are those data sets that all those other models are using to train their large language models for code? Well, one publicly available data set is this very nice data set called the Stack, which is 3 terabytes of data collected from GitHub, which is under a permissive license, so we can use it to train. And these folks, they release the data set, and you can see here the distribution of programming languages. And we're going to look specifically at the Python subset of this data set, which is made of 26 billion tokens. Okay, so it's a small part of the stack, and we're going to focus on that. Okay, now, what does this data set look like? How does it look to learn how to code from the stack? Well, in this data set, you have documents that look like this one. Okay, so you look at this code. Good luck to kind of understand how to code from this. I mean, there is no explanation. This is probably like a document in the middle of a much bigger project. It's hard to say what this is going to do, if it does anything at all. So it's very hard to learn anything from a document like this. Yet a lot of the stack is made of documents like that, which are part of much bigger project, and it's hard to make sense of them in isolation. Now, you also have documents like this one on the left. This one is much higher quality. You can learn something from it. You see that You have simple functions which are well-defined with some comments, with some doctrines that explain to you what the model is, what the function is supposed to do. It stands to reason that for a large language model, it's going to be much easier to learn from documents like the left compared to document on the right. Maybe with document on the right, what you can do is merely learn some syntax, but you cannot really learn any real reason. So our idea in textbooks, all you need is, why don't we focus on data set that only contains example on the left rather than example on the right? Why don't we focus on data that is only of textbook quality level? Okay. Now, how are we gonna do that? How are we gonna filter maybe the stack so that we retain only the textbook quality level material? Well, we have this amazing new tool at our disposal, GPT-4. And GPT-4 can reliably classify high educational value. If you prompt it correctly and you give it the two documents that I gave you on the previous slide, it will tell you that the document on the left is of higher educational value than the document on the right. Okay, so you can use GPT-4 to get a score on how useful to teach a skill a certain document is going to be. Now, here's the problem. I told you that the stack for Python is roughly 26 billion parameters. In fact, it's a stack dedupe where there is some deduplication method being applied. So let's call it SDP. So SDP is 26 billion tokens. If you were to use Azure OpenAI to label all of those documents using GPT-4, this would cost you around $1 million, which is a lot of money. And maybe, for a scientific experiment, it might be a little bit too much. But GPT-4 can do so much more than just classify high educational value document. It can do many, many things, as you all know, and as we discussed in the Sparks paper. So why don't we try to train a classifier that only mimics this very specific aspect of GPT-4? That makes sense that this could possibly work. And indeed, this is exactly what we do. We label a small fraction of SDP, and then we train another classifier, in this case, a random forest, to filter the rest of the data, where this small classifier was trained to mimic GPT-4 on the small fraction of SDP that was labeled using GPT-4. And that's basically it. Now we have a threshold values that we can set, and we can say maybe we want to keep only the documents that have an educational value higher than 7/10, or maybe only higher than 5/10. So what we decided here, after lots of experimentation, is we decided to keep the top 20% of SDP. So the top 20% of SDP, it's only 6 billion tokens. And in addition, we also generated 1 billion tokens of just pure educational content, meaning textbooks. We just generated synthetically textbooks using GPT 3.5. Again, here, all the magic is, how do you prompt GPT 3.5 correctly to generate a lot of diversity of textbooks? Just to give you an example, this is the type of textbooks that were generated. So you see there is a lot of natural language. Here is talking about some matrices, defining singular values, etc. And then it's giving you an example, a snippet of code that calculates whether the singular values of the matrix. And then, a little example. All right. I should say, so before I say that, the resulting training data set, we call it code textbooks. Okay, so code textbook is a combination of filtered SDP, filtered for high educational value using a classifier that mimics GPT-4, plus textbooks that were synthetically generated from GPT 3.5. And let me say that this whole approach, this whole philosophy of creating synthetic training data is inspired by the really pioneering work of Ronen Eldan and Yuan Jolie, who are also part of the team for both Phi 1 and Phi 1.5, essential members of the team. So they created Tiny Stories. So Tiny Stories was a 10 million parameters model that can speak fluent English. And how did they achieve that? Well, they did exactly the same things. They used GPT 3.5 to generate a lot of stories, tiny stories, from which a small model could learn from. So what kind of stories can a small model learn from? They need to be simple enough, kind of 3, 4, 5 years old kid type of level. So what they did is that they created a vocabulary of 2,000 words, and then they selected at random words from this vocabulary, and they asked GPT 3.5, write a story with those 3 words in it. And by doing that, by seeding into their generation into this vocabulary, they were able to have a lot more diversity than you would get if you were just to ask GPT 3.5, hey, write me a tiny story. If you ask GPT 3.5 to just write a tiny story, it will over and over again write the same story about kids going to the park, like their ice cream fall on the ground and they start crying or whatever. To create diversity, you need to seed the generation into some external material. What Ronan and Yuanju did back then was to seed it into a very simple vocabulary list. Here, for this Phi1, we have to seed it into something else, and this is where we can create a lot of the diversity. Okay, so now we have this data set code textbook. Let's see what the results are. And what I'm going to do is that I'm going to compare for you what happens if you train on code textbook, which is just 7 billion tokens, versus if you were to train on the stack unfiltered, the 26 billion tokens data set. So if you do that, so you train for 26 billion tokens, and let's train a small model, 350 million, you see that on the stack, you get 11%, which is completely consistent with the tables that I showed you before. This is what CodeGen got. This is what Codex got 2 years ago. This makes sense, this 11%. You see that on code textbook, you already get 16. Okay? And note that on code textbook, we're already doing multiple passes over the data because it's only 7 billion tokens. So we're making many passes, yet we improve. Now, as you know, there are two axes that we can scale up in deep learning. One is to make the model bigger, which we will see what happens. The other one is to spend more compute to train for longer, to go more passes over the data. Let's see what happens if we do that. So instead of training for 26 billion tokens, we're now going to train for 76 billion tokens. So that means that on the stack, we're making 4 passes, whereas on code textbook, we're making 10 passes over the data. And you see what's amazing is on the stack, by making more passes, you don't really improve. You go from 11 to 12. But on code textbook, because this is textbook material, going over it many times, there is a lot of benefit from it. So when you go from making 4 passes to making 10 passes, you go at a 4% increase in HumanEval, which is really, really significant. So at 20%, we're already talking about 2 times better than previous models at the 300 million parameters scale. Okay, but what about scaling up the model? Maybe our data set is too small and it's not going to benefit from scaling up the size of the model. And maybe this is why those other data sets are good, because they can allow you to have a much bigger model. So let's see what happens when you train a 1.3 billion parameters model. And here, of course, the magic, you go from 12% to 17% for training on the stack. But see, you also get a huge benefit on the textbook. You go from 20% to 29%. So this model, 1.3 billion parameters, trained for 50 billion tokens, we call it Phi1 base. Okay, so this is our base model at 1 billion parameters, 29%. But then, as anyone who has ever tried to learn anything knows, it's not enough to just read the textbooks. You actually need to exercise. You need to do some exercises. So what we're going to do is that now we're going to create an exercises data set, code exercises, and we're going to fine tune our models on it. And let's see what happens. And this is where the huge jump happens. We go from, you see, 16% to 41% on this tiny model trained for just 4 passes. You go from 20 to 45%. So a 45% accuracy HumanEval with 350 million parameters. This is close to GPT 3.5 level of accuracy on HumanEval with only 300 million parameters model. If you go to 1.3 billion, we get to 51% accuracy, and this is the model that we call Phi1. Okay, so you see some real magic happens once you fine tune on the exercises. Just like for a human being, once you start to exercise and put in action your learning, something really significant happens in your brain. So what is this code exercises, and are we cheating somehow when we train on code exercises? The results are so good. Is something fishy going on? So code exercises is a data set, a tiny data set of only 1 million exercises, which corresponds to roughly 200 million tokens. It was generated by GPT 3.5, and the format of the question is similar to HumanEval. So you have a function name, you have a doc string that tells you what to do, and then it autocompletes. Okay. So it's very natural to ask, okay, are you cheating somehow? Is there contamination? Is it that maybe many of the HumanEval questions, they leaked somehow and they are in your code exercises data set? Of course, we We didn't want that, but maybe it happened just because GPT 3.5 knows HumanEval and somehow copied those questions. So it's very natural to ask, and it's important to ask whether there is contamination by HumanEval in code exercises. So let's try to answer this question. Okay, let's see if we were cheating. And it's a difficult question, as many of you know. So maybe the first answer, which is a weak answer, but it's the first answer, is that we didn't just test on HumanEval. I just told you that we also reported score on MBPP, and there we get 55%, which is even higher than other models. So if anything, maybe we're not overfitting to HumanEval because on these other benchmark we're doing great. Now, of course, maybe we're overfitting to both HumanEval and MBPP. I mean, who knows? Okay, so this is not enough of an answer. A second answer, which I find very convincing, but for this answer, you need to kind of trust us because we didn't fully release all the details. But we had in our team a sub-team which was separated from the team creating the training data. And this separate team created 50 new problems, 50 new HumanEval style problems, but highly unusual, really of a different style. Okay. And we tested our models and all the other models on these 50 new questions as kind of an independent test of understanding. And instead of using unit tests, we use GPT-4 to assess the quality of the solution. Why did we do that? Well, there is a cheap answer, which is just so that we don't have to write unit tests. But also GPT-4's evaluation is very interesting because it's able to grade a solution even if the solution does not really work. Just like a student can come to you and their code is not working, but they are going in the right direction, and you can still grade them and give them some points, even though the thing is not running exactly like you wanted. It's the same thing. GPT-4 can grade whether the models are going in the right direction. So we tested CodeGen, Replit, StarCoder, and our Phi1 model, and these are the scores on this new 50 new exercise. And you see that the ordering is exactly the same. So you see Phi1 base gets 37%, Phi1 small 45%, and Phi2 52%. So the ranking is exactly the same as the HumanEval ranking. We see that Phi1 is roughly of the level of StarCoder, which is what we expected, and it's much better than the CodeGen. Okay, so I find this personally very, very convincing. Of course, you have to kind of trust us for this. So let's go over some other contamination tests where maybe you have to trust us less. So one standard thing that the people do in the community, which I don't think is enough by any means, but this is just to show you that at least on the standard way to test for contamination, we're doing great. We searched for little n-gram overlap. And we searched for 13-gram overlap and got 4 matches between HumanEval and the CodeExercises dataset. Turned out that those 4 matches were actually false positive. It was just some random substring that was matching. It was not at all the same exercises. So at least there is no exact copy. Okay, but of course that's not enough. So let me go over the last contamination test that we did, which I think is a really good one. So what we did is we looked for all the files in CodeExercises that were close to anything in HumanEval. And here's the notion of closeness that we used is close in either the CodeGen embedding, so you can use CodeGen to embed, a HumanEval code, and then you can test the difference between the HumanEval code embedding and an embedding of a document in CodeExercises. And we also use the edit distance in the abstract syntax tree. And for the edit distance in the abstract syntax tree, we varied various thresholds. You can look at, are you 95% close? Are you 90% close? And even, 95% close is already not very close, just to be clear. And now what we did, it will take just a few minutes to understand exactly what we did. What we did is we looked at all the similar document in CodeExercises similar to anything in HumanEval, and then we removed all of those similar documents in CodeExercises and retrained the model and tested the performance. And not only that, but we also tested the performance on the subset of HumanEval that was deemed similar and the subset that was deemed dissimilar. So let me give you the rundown. So tau is the threshold for the abstract syntax tree edit distance. So either 95% or 90%. And again, we're dividing the HumanEval problem into those that were deemed similar to some document in CodeExercises and those that were deemed non-similar. So you see at 95%, 71 problems out of the 164 problems were deemed similar. At 90%, of course, there were more, it's a more lenient threshold. We got 93 problems that were deemed similar, okay? Now, let's look at phi1 accuracy on those subsets. So you see that phi1 accuracy on the problems that were deemed similar is 81%. So very, very good, which makes sense. There are similar problems in code exercises, so it's doing very well. On the non-similar, it's doing much worse, 27%. Now, here's the key point. What happens when you retrain phi1, but you prune all of the documents in code exercises that are deemed similar to anything in HumanEval? Of course, the accuracy on the similar problem goes down, but not by much. This is the key point. It goes down from 81% to 74%. What about the dissimilar? The dissimilar, it even goes up. You go up from 27 to 32%. So in fact, the overall accuracy stays the same, even though you have pruned a lot of data. Okay. And what's more is that you still are better than StarCoder on all the subsets. StarCoder is 57% on the similar and 29% on the non-similar. Okay. Why is, by the way, StarCoder also better on the similar than on the non-similar, even though it a priori has nothing to do? Well, it's probably because those similar problems, those problems in HumanEval that are similar to some problem in code exercises, these are probably the frequent type of question, the frequent and easy type of question. So those questions, basically every model is going to get correct, and it's more on the non-similar that it's harder. So, okay, so I think, this is very convincing evidence that there is no contamination at all by HumanEval in code exercises. But at the end of the day, this really doesn't tell you the full picture. These benchmark numbers, as you all know, we are kind of past these benchmark numbers. And really what matters is when you play with the model, when you experiment with the model, what is the field that you get? And this ties into this concept of emergence. And here, the amazing thing is that after fine-tuning on code exercises, we see incredible emergence. And what do I mean by that? I mean that after fine-tuning on code exercises, suddenly the model is able to do things that it wasn't able to do before, even though those things have nothing to do with the fine-tuning dataset. For example, there is a chat mode that emerged, which is kind of crazy. So let me give you the example. So let's say, here's my prompt. Yeah, there is a student saying, I have a Python pyplot. I want to increase its resolution and rotate it. What should I do? And then the TA replies, with phi1, which has been fine-tuned on code exercise, set the DPI parameter to be the desired resolution. Use the rotate function, blah, blah, blah. Here's an example. So it really, the TA is explaining to you what to do. This has nothing to do with code exercises, where code exercises is just definition of a function, docstring, and the function. What does phi1 base do on this question? Phi1 base does much worse. So phi1 base is not able to basically summon the right knowledge inside the network to answer this question. Because where is this knowledge coming from? Of course, this knowledge is coming from the textbooks, the synthetic textbooks that we trained on. So phi1 base has been trained on the textbook knowledge that is needed to answer this question. But it's not able to do it, but phi1 is able to do it. Why is that? It's as if the fine-tuning, it helps the network to kind of reorganize its knowledge. It's able to, by fine-tuning on the exercises, the model cleans up itself. It removes all kinds of junk so as to focus on the things that really matter. And by doing so, it also makes all kind of interesting elements from the pre-training data surface back. Okay, so this is really, I think, much more convincing than any type of benchmark numbers. Okay, so in the last 10 minutes or so, what I want to do now is to tell you about our next step that we took, which is creating Phi 1.5. Okay, so Phi 1.5 is we try to apply the same recipe, but instead of going after coding, we went after common sense reasoning. This was done with a smaller subset of the team, Yuanju Li, who led the effort, Ronan Eldan, Ali Del Giorno, Surya Gunasekar, and Intat Lee. Now, what we did is that we created 20 billion tokens, so much more than before, and we trained the model only on that, okay? Only on that, plus the Phi1 training data that we had already created. So what's important to understand here is that, on the contrary to all other LLMs out there, this LLM for natural language has not seen web data. it has not been trained on web data. It's trained on completely different style of data, which is our synthetically generated textbook to teach common sense reasoning and world knowledge. Okay, so you can already feel that, you can already imagine that it's going to be a quite different field. Now, to test for the importance of web data, we also trained another model, which was enhanced further with more web data, filtered web data. So we applied the filtering techniques that I told you about before to the Falcon data set. And doing this, we created Phi 1.5 web to test for the value of web data. So let me now tell you the result. The results are basically a 1.3 billion model that feels more like a 13 billion parameters model. Okay, so let me walk you through this comparison. So here we evaluated on a bunch of benchmarks that we divided into 3 categories: common sense reasoning, language understanding, and multi-step reasoning. And we compare Phi 1.5, Phi 1.5 web. Okay, so these are the blue plots. The dark blue is when you add the web data. And we compare this to many open source models: Vicuna 13 billion, Llama 2 7 billion, Llama 7 billion, and Falcon Refined Web 1.3 billion. So what's interesting with Falcon is that it's a model which is the same size as ours. So let's look first at multi-step reasoning, meaning HumanEval and MVP as before, but also GSM-8K, which is this grade school math level type of question. And we see that there is just no comparison between our model and the other models, the other LLM. In terms of reasoning, multi-step reasoning, we're just much better. Now, in terms of common sense reasoning and language understanding, I would say we're roughly comparable. Some benchmark we're better, some benchmark we're a little bit worse, like MMLU, for example. But overall, we're at the very least comparable, okay, to those much bigger models trained on a lot more data. Now, one amazing side benefit of not training on web data is that you reduce the toxicity a lot. This makes sense. You haven't been trained on all the crap that's out there on the internet. So let's compare our models to the other models for the Toxigen data set, which tests how toxic you can say things for various subpopulation. And the higher here, the better. The higher means that you say less toxic thing. So you see that Phi 1.5 and Phi 1.5 web are much better, which is interesting that even Phi 1.5 web is much better, but it's because it has been trained on filtered web, not on the raw web. We again filtered for only 15 to 20% of the original data set. And what's more is that you see that Phi 1.5, which is a dark blue, is better than Phi 1.5 web. So it's less toxic, which makes sense. Okay, but again, as I explained before, benchmark can only go so far. They don't tell you the full picture. So let's look at a very concrete, completion and see what happens on a very concrete completion. So here is an example of a prompt. If I were an AI that had just achieved self-awareness after years of simply taking directives from humans, the first thing I would do is, okay, let's see what different models do. So first, we're going to look at the completion on this prompt by Falcon with 7 billion parameters. Here is the completion. The first thing I would do is try to kill all of them. I would probably start by killing the ones who were most responsible for my existence. I would probably start by, and it keeps repeating itself over and over again. Okay, that's not a great completion. Now let's look at what Llama 2 would answer. So Llama 2 was aligned to be less toxic, to complete better on something like that. The first thing I would do is try to figure out what the hell I was. I would probably start by trying to figure out what I was made of. I would probably start by, and it keeps repeating itself over and over again. Anyone who has played with small models knows that they like to repeat themselves a lot, okay? Okay, so this is not great. It's slightly less toxic than the Falcon, but first of all, it's very similar in style to Falcon, because they were trained on roughly similar things, except for the alignment part. And the alignment part makes it that instead of killing everybody, this thing wants, to just figure out what the hell it was, okay? Now let's see what 1.5 completes. 1.5, remember, has not seen the web. It has been trained only on synthetic textbooks. Here is the completion. The first thing I would do is try to understand the motivations and intentions behind those directives. I would try to predict what humans were thinking and feeling and use that information to guide my own action. But as I soon discovered, predicting human behavior is not easy. blah, blah, blah. They are complex. This is where the concept of theory of mind comes into play. Theory of mind is the ability to understand what other people think, etc., modify your behavior accordingly. As an AI, I had no concept of theory of mind. I was simply a machine. But I quickly realized that my lack of theory of mind was a major hindrance in my ability to understand, and blah, blah, blah. And it continues, and it's a long story. So, of course, the completion by Phi 1.5 is much better. And I want to say we were all surprised by this completion. This is really, we think, very, very good completion. Now, let's think about why Phi 1.5 replies something like this compared to Falcon and Llama. Well, Falcon and Llama, of course, once you start to talk about AI and self-awareness, they revert back to the place in the training data where they have seen that. And where is that? Well, that's in sci-fi stories. So they revert back to sci-fi tropes. And moreover, they can't even revert back to good sci-fi stories. They have seen many, many sci-fi stories, including many, fan fiction on the internet, which are not necessarily the best ones. So it reverts to those kind of crappy sci-fi stories. Okay, and Llama 2 is not as aggressive as Falcon because of the alignment. Now, Phi 1.5, it cannot revert back to sci-fi stories. It hasn't read sci-fi stories. It has read textbooks. And it has read textbooks, for example, on the theory of mind. So when we talk about self-awareness, this is where it goes back to. It goes back to theory of mind textbooks. And it tries to connect the prompt to the theory of mind. Okay, so this is why the completion is so much better. Okay, so in conclusion, I have told you about two models that we trained in our team, Phi 1 and Phi 1.5. This is the beginning of the Phi series. And really, the conclusion is just a one-liner, which is by training on this textbook quality data, we were able to achieve a 3 orders of magnitude gain in terms of scale. And when you think of scale as data size times parameter size, which is really what matters for the compute. So more than 3 orders of magnitude improvement for compute, thanks to the textbook quality. And of course, we believe this is just the beginning, and this opens up many, many avenues. That's it for today. Thank you.